Good morning, everyone, or good afternoon, depending on where you are joining us, and welcome to today's webinar. My name is Seth from Business Review, and I'll be your host. It is our pleasure to have Anexa with us today, who'll be presenting this webinar entitled Fair Play and Efficiency Guarantees. Today's guest speakers are Peter Hartner and Joseph Pettit.
Good morning or good afternoon all around the globe. We have many guests from all regions in the world. I'm happy and pleased to welcome you to our webinar, Fair Play in Fuel Efficiencies. My colleague Peter Hartner and myself want to give you an introduction to fuel demand models and settlement systems. So first, I want to give you an introduction to our company, Anexa, very brief, and then I want to go into our topic, introduction on why and how fuel demand models are applied. And then I want to hand over to my colleague Peter Hartner, giving you more technical detail on the thermodynamic modeling that we apply and on how a fuel demand model is running online. We want to conclude the webinar with a short summary of Anexa experience. And most important of all, we want to be answering questions that you may have. As Cesc mentioned at the beginning, there is an option to enter questions for the Q&A session. And I want to also invite you to type in your questions. We will try to have enough time to answer all of your questions within this webinar. Anexa, our company name, is actually an abbreviation that we chose, Energy Expert Software Applications. And this name, in short, actually quite nicely comprises our qualities because we are a mixed team. We have energy experts, process engineers, mechanical engineers that are specialized on process simulation for power plants. And we also have a large team of software engineers that that supports our tools in terms of the heat balance software, but that also develop applications around that, software applications that help us serving our customers with tools to ensure productivity, and also, as in this current webinar of today, in settlement systems and fuel demand models. So in a short phrase, as an elevator speech, Anexa provides expert consultancy and software systems for the power industry. As an overview of our portfolio, the current slide shows a few pictures of typical power plants that we work on. So we are working on combined cycle or combined cycle plants combined with seawater desalination, as in the upper left corner. We're working on heat recovery plants that generate power from exhaust gases, as in this example from a compressor station. Lower left shows the first solar power plant in the Middle East, Shams 1 power plant. And as our company is also participating as a consultant in many new projects on the so-called Energiewende topics, the electrolyzer picture in the lower right shows that we're also active in this field. And our portfolio comprises both the consulting based on thermodynamic simulation and systems, fuel demand models and settlement systems for independent power plants and independent water plants, plant simulation models in general, what-if models or planning models. We are co-developing a software, the Epsilon Heat Balance software, together with the owner of this software, Iconic Solutions of Germany. And based on such models, we also build software systems for operational support and optimization. But in most of our projects, the underlying part is a process simulation model, as shown on this slide. So with the Epsilon Professional Heat Balance software, we can model the power plant to the very detail. Peter will show more details later on in his part on the thermodynamic modeling. But any type of power plant, may it be fossil-fired gas or steam plant, cogeneration plants, renewable plants like solar, or even the latest processes including wind, solar, PV, electrolyzers, fuel cells, all of that can be modeled to the very detail with this Epsilon Professional Heat Balance software. And because of this flexibility in the modeling, we also have quite a mix of customers worldwide. As you can see on the map in the center of this slide, we have customers and projects all around the globe, from the west coast of US to Japan. And with the mix in our portfolio, we also have different topics. So with companies like General Electric, Mitsubishi Power, and Ansaldo, we are talking about heat balance software. NXA is developing a gas turbine library add-on and the reciprocating engine add-on for the Epsilon software. We support as a consultant companies like big utilities like NextEra Energy or Iconet Solutions, or OMV, voestalpine. This is steel and oil and gas companies in Austria. Calpine in the US is also a very prominent customer of us. But as you can see also on the map, most of our projects actually are located around the Arabian Peninsula. This is our main portfolio, the supply of settlement systems, fuel demand models, or our other plant performance models for independent power projects. The customers in this field, you can see the big names in this industry: ENGIE, Mitsubishi Corporation, Marubeni, Mitsui, Sumitomo, Sembcorp of Singapore, Mubadala, Aqua Power, Dhaka. So all the big players we've been in contact with, we've been in projects with. And so this concept of independent power production, independent water production as a public-private partnership project is a core of our portfolio. And as you can also see from the yellow dots in this map, the concept is also moving more to the east as well as to the west. In Africa, you see some plants, solar power plants. In Morocco, that's the Noor projects for the Noor 1, 2, 3 solar power plants where we supplied the settlement system. Or on the other end, further to the east, Uzbekistan, we have delivered a fuel demand model so far, and we are going to extend in this area as well. And we have been also introducing the first settlement systems to Bangladesh and Myanmar. So this market is moving also to the east. With that, I want to conclude on the company introduction and go into the topic of our webinar. Why and how are fuel demand models applied? As mentioned, we are talking about large infrastructure projects for power, or combined power and water, or power and steam. And these projects, the success story of this type of project started basically in the Middle East region, in Oman and the United Arab Emirates, when in the late 90s, the first independent projects were tendered. This is public-private partnership projects where the government cooperates with private investors to build such large plants. And the benefit of this approach is clearly evident from the economies in this area. There have been no power shortages, major issues, and also price-wise, the projects for power and water have shown that they are very competitive, and electricity and water can be supplied from these public-private partnership projects at a very competitive scale, while at the same time providing highest efficiencies and highest availabilities for these very important products. Such a public-private partnership project is based on purchase agreements. And these purchase agreements include also fuel efficiency guarantees to ensure proper operation and maintenance of these power plants or power and water plants. Fuel efficiency is even more important in those countries because the fuel is supplied from the government and electricity and water are purchased by the government. So the plants are actually converting the energy form, and it is most important that the initial guarantees on fuel efficiency as well as on the degradation of those plants are in line with the contractual guarantees. And for that purpose, settlement systems and fuel demand models are required for all of these independent plants. And the settlement systems are set up to do an hourly accounting for production and fuel consumption. So every hour of operation, the plant is measured, the metered data, the meter increments are calculated, and by the end of the month, beginning of the next month, the independent power plant, independent water plant can create an invoice that really does this hourly accounting and calculates the tariff as per the purchase agreement. And so these tariff equations also include fuel payments, and these fuel payments may be established as a fuel guarantee with a bonus penalty system, or simply that the plant is paid for whatever the guaranteed performance is as per the contract. So if the plant deviates because the equipment was not maintained properly, or if it is operated in an incorrect manner, then the fuel consumption may be higher, and this is penalized by the fuel demand model. The comparison against guaranteed performance under all operating conditions is therefore included in those contracts and must be provided through a fuel demand model. The power purchase agreements as such include a single guarantee point, so-called reference site conditions, performance. But there are natural factors on fuel efficiency that need to be considered. A gas turbine plant is very much influenced by ambient conditions. Ambient temperature, pressure, humidity influence gas turbine performance. The cooling water temperature on the condenser side influences the performance of the steam turbine. So ambient conditions are there by nature, and of course the operating company, the project company, must not be penalized if ambient conditions are changing. So there must be corrections for ambient conditions. Other factors from operation, like fuel type, fuel, heating value, grid frequency, or the power factor, external factors that are not under the control of the plant, of course, they influence the efficiency as well, and they must be corrected. And most important, the reference site conditions are typically at a baseload point with a maximum output. Such operating modes are not the normal operation of the plant. Normally, plants are dispatched according to the demand. They are kept at certain operating modes by the dispatcher. And so the equipment configuration may change. The output level is, of course, following the dispatch instructions. So the plant is not operating under the reference conditions. And thus, the guarantee value must be corrected to reference conditions. So the only output that is required from the fuel demand model in total is actually just one factor, the correction factor for specific heat rate. How is the reference site heat rate applied to the current hour according to the current operating conditions? So this is the task of the fuel demand model, and that must be achieved. How is that achieved? Well, there is different options in the correction methods. For a very simple plant, a table may be sufficient. The contract simply includes a table how these ambient conditions or operating conditions influence the plant output and heat rate. there may be correction curves with the plant, so a little more in complexity. If it becoming, if fuel efficiency is a result of several factors, it may be equations that fit. But in fact, it turned out that for a full-scale power plant project with several generators and large equipment, fuel demand models are the proper approach. So let me introduce you to fuel demand models as such. In general, they are process models. Still, they include some correction curves, and I take this as an example on explaining how a correction curve works. On this slide, you can see gas turbine baseload correction for heat rate. So on the x-axis of the left-hand side graph, you see the inlet temperature to the gas turbine, ranging from minus 35 degrees to plus 50 degrees centigrade in this curve. And on the left-hand axis, on the y-axis of this graph, you have a correction factor. This is a correction factor for heat rate. The heat rate is defined in the so-called rating of the gas turbine. The rating consists of power, heat rate, exhaust flow, exhaust temperature, sometimes additional parameters, but this is the core rating data for a gas turbine that you need to specify the performance. And the heat rate at rating conditions is 9,836 kilojoule per kilowatt hours in this example. And it's important to understand ratings are only valid at a specific reference condition. So the T1 inlet temperature shown on the lower right is 15 degrees. So at 15 degrees centigrade, as indicated with the red arrows in the graph, we have a correction factor of 1. So if the gas turbine is operating at 15 degrees, heat rate will be exactly the number as stated in the rating. If, on the other hand, ambient temperature is much higher, like here 40 degrees centigrade, then the heat rate will increase. So it will consume more kilojoule of fuel energy per kilowatt hour of electricity, because hotter intake means there is more volume flow through the gas turbine, there is more losses to the operation. So relatively, the fuel consumption will increase just because of the ambient temperature. And this can be corrected here with this type of correction curve for the baseline correction heat rate versus inlet temperature. There's, of course, many other factors that influence the gas turbine. Gas turbine baseload correction include as a minimum, as shown in this slide, inlet temperature, ambient pressure, inlet pressure drop, exit pressure drop, relative humidity, and grid frequency. Maybe even other parameters influencing the performance, like the water injection flows for power augmentation or NOx control, things like that, may also be added to this set of correction curves. And the key performance parameters of the gas turbine, power, heat rate, exhaust mass flow, and exhaust temperature, as shown on this slide, they all have different dependencies on these parameters. So in this case, you have 4 times 6, already 24 correction curves for these parameters to adjust the output for a specific influencing factor. In addition, if the gas turbine is not operating at base load, at full load, there is part load corrections. Typically, they include heat rate, exhaust flow, exhaust temperature. So if we look at the middle slide here, for this gas turbine, the exhaust flow that is because of the operation of inlet guide vanes, the exhaust flow is reducing with the load fraction up to a certain minimum value where the inlet guide vanes are close to the maximum extent. The effect of this change in inlet guide vanes can be seen on the right-hand slide, on the right-hand graph, with the exhaust temperature. This is going up with part load fraction because of this throttling of the inlet flow to the gas turbine. So there's a lot of interdependence of parameters in the gas turbine, and all of these curves that I've shown so far just cover one gas turbine. So when looking at an overall plant, you can now imagine that it would be a very, very long list of individual correction curves to be applied. And also there's a lot of data that are not applicable, that are not available as a correction curve, but that are result of a heat balance calculation anyway, like steam production or other parameters that are a result of the process conditions. So it will be becoming very complex to simply put that into correction curves only. As an example of overall plant performance curves generated from a model, here you can see some performance test correction curves that are valid for baseload, because this is the way that the performance test is performed at maximum output, maximum operating output. The fuel consumption is determined and the respective corrections are applied, because test conditions typically do not exactly match reference conditions, and so differences in ambient temperature, humidity, pressure must be included in a correction procedure to determine the values at reference conditions. And of course, such plant corrections are only valid for a particular configuration of the plant. Everything operating, any extractions or product flows at a specified reference conditions. Part load correction curves for a power plant are actually very specific, because, as explained earlier, there are so many influencing parameters on performance. You can specify part load performance only at particular ambient conditions. So the graph shown in this slide for a combined cycle plant in combined cycle and simple cycle operation in terms of heat rate correction factor is only valid for a fixed set of ambient conditions in terms of temperature, pressure, ambient humidity, grid frequency, and power factor. Any parameter of these ambient conditions and operating conditions changing would change the shape of the curves. And you can see that there is a factor of 1 only for full output in combined cycle mode. That's the end point, the most right end point of the combined cycle operation in 2 gas turbines. And then heat rate is increasing, and you can see that there is 4 options: combined cycle with 1 gas turbine in addition, and then 2 gas turbines, 1 gas turbine in simple cycle. The values are relative. The factor in relative heat rate is here relative to the heat rate at full load with 2 gas turbines in combined cycle mode. So this type of curve is only valid at particular ambient conditions for selected configurations. So in this case, one of these 4 curves, but also for identical loading of units in the blocks only. Would the plant operate one of the 2 gas turbines at different load level, then the curve is not valid anymore. So it is becoming quite complex to put that into a correction curve. So at the end, we come to a conclusion that for large IPP with typically multi-unit configuration, operating options that are very wide, like additional duct burners, different modes of operating the cooling system, the application of inlet chillers, or desalination units that may be on or off in the equipment, and of course prevalent operation at part load, which is a typical way you operate a power plant to follow the demand and dispatch. Then there are simply too many combinations to allow for a curve-based approach. So this is why the fuel demand model was selected as the valid correction procedure for a power purchase agreement. And with that, I want to hand over to my colleague Peter Hartner to give you more details on the thermodynamic modeling with Epsilon Professional, which we apply in our fuel demand models.
Thank you, Joseph, and a very warm welcome from my side as well. Now we are talking about the thermodynamic modeling, and Enexa as a company uses the Epsilon professional heat balance software to produce such fuel demand models. And as Joseph has already mentioned, those fuel demand models have been introduced to work around the hassle with all the different combinations of correction curves, which may be a possible task to solve for a correction procedure for such a large scale IPP or IWPP project. The thermodynamic model must be configured so that it can cover all the different operating conditions which the plant can run at, all the different plant configurations, including simple cycle and combined cycle, and most of all, the FDM must accurately reflect the PPA guarantees. So the guaranteed figures, or the guaranteed performance which has been agreed in the PPA or in an ECA, an energy conversion agreement, must be respected by the FDM. Usually, there is a requirement in the contract that such a fuel demand model is audited by an independent third party, so that all concerned parties, so generating company and off-taker, are ensured that this model is correctly reflecting the guarantees of the PPA. And it does also help to comfort the lenders and any financial auditors which may look at this project. So on the previous slide, you have just seen the top layer of such a model, but the model is including much more detail than what you could see from the top layer. So each individual unit is modeled to a great level of detail. And on this page, you can see the gas turbine. And the gas turbine is including all the OEM correction information, which Joseph has already presented in his part of this presentation. So each GT is being modeled separately, and it's covering the OEM performance, and it does also respect the PPA guarantees. And we will come back to that later, what it means to respect OEM performance and PPA guarantees at the same time. All units must be modeled independently. So it is not sufficient to have like one GT modeled and multiplied with a number of operating units, because each of the GTs could run at a different load level. It could even use different fuels, or the inlet conditioning, air inlet conditioning could be different for the different units for whatever reason. In the same way as the gas turbine, Enexa also models the HRSG to a great level of detail. So each heat exchanger surface is modeled separately. Duct burners are modeled separately. The cold and temperature control is modeled as per the design philosophy coming from the EPC, and so on and so forth. So considering all those different heat exchanger surfaces and the proper configuration allows the model to behave in the very same way as the physical plant. So loading of individual steam turbines with different pressure feedback to the HRSGs, etc., can be covered. And again, therefore, it is important to have every unit of the plant being modeled separately. So it's not sufficient to just model one train and then multiply with the number of units in service. Steam turbines are modeled so that every spool of the steam turbine is represented separately in the model. This allows to account for any admissions or extractions for product steam or for steam returning from a customer, and also the cooling systems for the steam turbines are modeled separately, so that basically this whole thing behaves, the whole model behaves in the same way as the physical plant. So when talking about FDM model versus correction curves, one needs to consider the following things. In a plant, the GTs may be loaded individually. The inlet air treatment of the GTs may be operated in different ways for the different GTs. Different fuels might be used for different GTs even within the same block. And simple cycle and combined cycle operation may be combined at the same time. Different loading and inlet pressure control for SDs has already been mentioned, and also admission and extraction from steam turbines. So all these aspects are manageable with one single heat and mass balance model, or alternatively with an almost infinite number of correction curves. So it's a much easier task to cover all the different ambient loading conditions and configurations with a single model, because the model basically behaves in the same way as the plant. So it's basically a twin of the plant, an electronic twin, whereas for the correction curves, you require this many curves that it's impossible to do this correction task within due time. So you also need to consider that for creating those correction curves, you need a heat balance model anyway. So why not using the model in the first place rather than coming up with a huge number of correction curves with a very complex process to get the correction factor, instead of just running one model and having the correction available right away. So there are certain requirements, required information, so that one can build a fuel demand model. Of course, you need the OEM performance or correction information, so that the description, the performance description, the operational performance of the unit can be properly represented in the model. So this is true for the gas turbine, HRSG, steam turbine cooling system, and also for the major balance of plant equipment. The design and the off-design plant heat balance diagrams are required. This allows to identify any control strategies which need to be implemented so that the fuel demand model behaves in the very same way as the physical plant. And finally, you need to know the fuels and the impact of the fuels on the equipment, especially for the gas turbine, compositions and heating values and the limits for those different types of fuel are required. And you need to know the foreseen operating and ambient conditions limits so that the model can be configured in a proper way. And finally, you need to agree, or you need to know on the agreed auxiliary load model, because the model should calculate the guaranteed or the projected fuel demand for a given operating scenario. And the auxiliary load model is also one of the important things to be factored into the FDM, so that there is no over or undercompensation of fuel when it comes to misconfiguration of the auxiliary equipment at the plant. Furthermore, you need to know the operational limits, so maximum duct fuel energy consumption or maximum gas or steam temperatures, so that one can set up the proper control strategy in the model, so that duct fuel, bypass flows, letdown flows, etc., are not exceeding a limit, so that the fuel demand model will not give an infeasible result, or it will not simulate a case which cannot be accomplished or where the plant cannot be operated. The plant guarantee values are important, as Joseph already mentioned, because at the reference site conditions and also at a few operating points which are pre-agreed in the contract, the model must respect the guarantee numbers which have been specified. in the PPA or ECA. The anticipated modes of operation and the associated control philosophy is important, as mentioned, so that the model does behave as an identical twin of the plant as close as possible. Now, as Joseph mentioned earlier already, the most important task or the most important criterion for the FDM is that it must match the contractual guarantees. Right? So, on the one hand, the model should match the OEM performance as close as possible. So the plant or the model should behave in the very same way as the plant, and it should show the very same physical behavior of the plant. But most of all, it must match the contractual guarantees, or it must not exceed the contractual guarantees. Now, as we all know, in order to be successful in a tender, sometimes there are commercial decisions being made, and offered numbers or guaranteed numbers are somewhat aggressive, and sometimes the conditions 1 and 2 on the slide are contradicting this condition 3. So the only thing one can do in this case is to bridge the gap as much as possible with a flexible model, but in no case the model can exceed the contractual guarantees. So, number 1 condition must be you have to match the contractual guarantees, and then the model should match the OEM performance as close as possible with the same physical behavior as the plant, while respecting the contractual guarantees. So this is the paramount condition for a fuel demand model. I've already mentioned that an independent auditor, independent third-party consultant should be assessing the FDM. So to get reconfirmation that the FDM is in compliance with the PPA, it provides a double verification of the model by a neutral party who has no interest in shifting performance in either direction. It does also allow to get confirmation of the correct online implementation to satisfy lenders and financial auditors to assure that the model, which has theoretically been tested against the OEM curves, is also properly implemented to be fit for operation throughout the term of the contract. Now with that, let's come to online fuel efficiency calculation and what is to be considered when doing this. There are a few challenges in online mode. So when you run a model in offline mode, the operator of the model has certain means of interventions, but for online operation, the model must converge reliably under all possible conditions. Also, the recalculation of a large number of cases after correction of input data or after an outage of the hardware must be possible within a reasonable time frame. So, in order to accomplish this, one needs a robust model. So this is the first and most important condition. You need a robust and a flexible infrastructure so that a large number of cases can be calculated in parallel if required. You need high-end hardware so that you're not prevented from operating the system throughout the term of the contract. Because too many outages of the system will not allow you to reliably calculate your FDM cases, thus meaning you cannot create your invoice at the end of the month. And you, of course, also need proper input signal treatment, so quality and range checking. Do not even start FDM cases with invalid or inconsistent input data, because that would not lead to a valid result anyway. So to safe resources, proper data management is also of essence. So how are we ensuring reasonable results? One thing very important is input data range checking. So it is of essence that the parties work together closely in order to define the range limits for the various parameters which are input to the FDM. Then when it comes to modeling, input data consistency checks must be applied to ensure that the model does have a chance to converge. And of course, transparent reporting of configuration or data inconsistencies must be included in such a model. So this goes far beyond the thermodynamic modeling. It's really relevant for the whole infrastructure and for the whole system, for the whole settlement system and fuel demand model. And finally, if you cannot find a solution, you must have replacement strategies in place for invalid FDM results so that you still can do the hourly calculations, the hourly accounting for fuel, even though the input data did not allow for a calculation of a valid FDM result. There are certain key qualities which such a fuel demand model must fulfill. The one is detail. So you must match, the FDM must be able to match all the possible configurations. Accuracy, you must have undisputed results. So you must be able to tune the model to match the OEM performance data and correction curves and OP points as close as possible. Reliability is very important. So the FDM must produce reasonable results whenever possible based on the input data available to the system. And it must be very easy to use. So you require online infrastructure and offline infrastructure so that you are very flexible when it comes to troubleshoot any of the input data and provide a valid FDM result for most of the FDM cases. And it requires scalability. So the system must be designed in such a way that it allows reasonable recalculation times. So in case of a data outage or hardware outage, after some time, you need to recalculate the FDM cases for the month in a reasonable time so that your invoice calculation or invoice creation at the end of the month is not disturbed or delayed. With this, I'm handing over to Joseph again and let him talk about NXA's experience.
Thank you very much, Peter. For the sake of having enough time to answer your questions in the Q&A session, I'll keep that very short. NXA started in the year of 2007 in the Middle East region with the first projects in the UAE, Fujairah 1. So more than 15 years, we are active in this field of settlement systems, fuel demand models. As a technical advisor to project companies and bidders, we have also modeled plants in which the winning company was a different one. So we've participated in tenders, built models for a lot of more plants than actually FDM running. But that is the competitive nature of this market. Nevertheless, we are of course in the position and capable of building the FDM, even if we are not the technical advisor to the bidder. So any contractual guarantees can be met exactly from our modeling, even if the heat balances and OP values have been created by others. As you can see, it spread our projects as well as the PPP market into other regions. We have many references in Saudi Arabia, solar plants in Morocco, but also a lot of fuel demand models for cogeneration plants recently, and I expect that to be one of the most frequent application in the future as many companies also consider cogeneration facilities under an IPP project. And of course, if we sum up our experience over the last 15 years, we end up with more than 30 gigawatt of installed capacity that are equipped with our settlement systems and fuel demand models. Total water capacity larger than 8 million cubic meters per day. So we have quite a large fraction of the market covered with our system. And as we also see, as we are a large, you saw the picture of our company, we are a real company. We are not a small company working from and using any freelancers. It is a company with full service team, and we've been asked for replacement of existing systems by vendors who have disappeared from the market or have not are not able to maintain the systems over the 20-25 years of a contract. So we have started to replace a few systems recently during the past 2-3 years, and we see continuous requests coming in this for this matter as the IPP market has grown older and first contracts are being extended. Also, we have successful deliveries over all types of power plants, so not only gas turbine-based plants, also cogeneration and combined power water, as well as solar plants. And also we have entered the sewage treatment plant market recently with a project in Saudi Arabia. So settlement systems and fuel demand models are expanding. Fuel demand models, of course, for power plants, but there is different types of performance models, plant performance models as they are called, electricity demand models for ISTP or IWP projects, and also for deemed electricity, deemed electrical energy delivery. There is models required, so-called solar performance models for solar power plants in case they are curtailed, that a respective adjustment payment can be claimed by the project company. With that, I want to conclude the summary of our references. A long list, you may see familiar names. Feel free to ask questions if you have any to a specific project. But with that, I want to end this summary. Thank you for your attention in this webinar, and ask Cess to moderate our questions and answers session now. We still have enough time to answer at least a few of your questions. And of course, all questions are recorded and we will respond to them individually after the webinar. Thank you very much.
Thank you very much, Joseph. Just a reminder for the audience, in order to ask questions, you can send them in via the questions widget. Just type them into the box at the top right-hand corner of your screen and click submit. Now we'll start our Q&A session. We'll start with this question. Can the FDM be adjusted if the actual fuel consumption of the plant is higher than expected?
Let me answer to that, Cess. The FDM is a contractual model, and it is a contractual guarantee, and as that, and for this reason, it is the rule of the contract that will override it. So there is actually, as mentioned in my introduction, it is the benchmark model for the guarantees, and it cannot be changed afterwards. So in an IPP project, if the initial guarantees were exaggerated, if they were too aggressive, and the plant as built cannot meet those fuel guarantees, then there is a problem, and of course also a financial problem, as the fuel guarantees will be, if they are not met, will be penalized under the contract. The only way to come out of this dilemma is an agreement with the off-taker to revise the FDM. That is a contract amendment, and because it was the result of a tender and other participants, other bidders were not chosen in the tender, the chances are very low that you can easily change your fuel guarantees afterwards.
Perfect, thank you. Another question we received is, can I use the FDM for monitoring the performance of my plant?
Let me answer this question. This is Peter. The FDM, fuel demand model, is not a performance monitoring system. So it does only calculate what would be the projected fuel demand under the current condition, given the contractual performance. So it will only be possible to see whether or not your overall plant is performing better or worse than the contractual guarantee or the contractual projection. But the FDM is not designed to evaluate performance of individual equipment. That is a whole different task, and it would require a different system in order to do performance monitoring in the classical sense.
Great, thank you. And how long does it take to configure and deploy an FDM?
Well, it's usually a process of 6 to 9 months. Because this FDM deployment is not only, the modeling based on some design information. Usually, it takes some time for the project companies or whoever is responsible for providing this information to actually provide the information. It is also a question of agreeing on functional design specifications, getting approvals from the off-takers, etc. So, from our experience, this is usually a process of 6 to 9 months. Depending on the off-taker and depending on the availability of the design information. And all what I said so far is valid for a greenfield project. It's a whole different story for existing plants where some of the information may not even be available.
Thank you for that, Peter. And another question from the audience. From the data of your experience, they are most in Middle East and Morocco being the only African country. Why are you not having experience from European, North and Central America power companies?
Well, that's easy to explain. It's simply because this type of public-private partnership projects is mostly applied in the Middle East region and Southeast Asia region. In Europe and North America, you have deregulated markets where the plants have to purchase the fuel at their cost, and they have to sell electricity into a market and to bid into a market. So there is no tariff equations applicable. It's just their business as a generator in a free market. So fuel demand models are only applicable if you have power purchase agreements. So in Europe and North America, you may find this type of purchase agreements with utility plants supporting a refinery, things like that. They may have contracts that include such guarantees. So far, we have not built a settlement system for such an application, but they are quite rare in Europe and US. The main market is, as I mentioned, these large public-private partnership projects in the Middle East, Southeast Asia.
Great, thank you, Joseph. Another question that we have is, if there is a discrepancy between OEM data and PPA, who do you follow?
Let me answer this question. It's very clear. If there is a discrepancy between OEM data and the guarantee data in the PPA, you must respect the PPA guarantee data. So the OEM data is very good and required and important to follow the operational behavior in terms of a trend. But the guarantee values of the PPA must be corrected. And that somehow somewhat relates back to the question which Joseph answered before. If guarantee values are provided and accepted, and if those the contract has been signed, you must respect those guarantee values. So OEM information is good and required in order to have the right behavior in terms of trending, but the absolute level is certainly dictated by the PPA number. And the OEM number can never overrule the PPA guarantee unless, as Joseph said, there is an amendment of the PPA or ECA, which is quite difficult to achieve.
Great, thank you, Peter, for the answer. Just a reminder for the audience, you can still submit questions via the questions widget. All right, another question is, correction curves provide expected performance at the point of operation. Hence, a reference point is set and deviation can be analyzed. How the thermodynamic modeling can replace it?
Well, can I also answer this question? See, the correction curve, this question lets me assume that the person asking the question assumes that the thermodynamic model is like competing with the correction curves in terms of validity and applicability. One needs to know a correction curve is always derived from a model. So it is not a model replacing a correction curve, but it is, you can derive a correction curve by doing a series of calculations, different cases with a model, and the results from the model can then be used to create such a correction curve. But it is not that the correction curve is the first thing to be available, and then based on that you can create a model. It must always be a model which is available in the first place. So when running a model in two conditions, number one, actual conditions, and number two, reference conditions, you get the same two results which you will find on the correction curve. It's just way more complicated to cover all potential operating configurations and conditions with correction curves, as Joseph explained in the beginning of this webinar, because you will need an infinite number of correction curves to cover all the different conditions and combinations of conditions, which can easily be achieved by a model. So it's not model competing against curve. It's simply that it's much easier to do the calculation with the model rather than creating all the correction curves where you may not even know which curves you require until you run into the operating scenario you're looking at.
Fantastic. Thank you, Peter, for that. Since we're close to the hour, I'll ask this last question, but please don't worry if your questions haven't been answered, as our speakers will get back to you. What about using AI machine learning for building an FDM?
Well, that's a very modern question. AI is, everybody's talking AI, the point is that artificial intelligence can only learn from data. So data have to be available. And so unless there is data measured of a plant of all possible operating conditions and all possible combinations of equipment in sufficient number, so you need really a lot of data to use to create a neural network or AI-based model, it's simply impossible. So, and second, an AI-based model, of course, is not explainable. There is no, you cannot look inside what is the physics behind that. It's simply representing a huge number of data. So the approach with the fuel demand model in a process simulation model is on the one hand fully transparent. Yeah, you can see all the behavior in the individual equipment, where it comes from. It of course follows the physics and the laws of nature, and it can cover all possible combinations within the entire technical possible range of all equipment. This is, in short words, impossible for an AI-based system to learn.
And may I add something here? For an AI system, if you train a fuel demand model, which is based on an AI system based on operational data. Nobody can assure that you are not including operating cases where the operation of the plant is less efficient than agreed or more efficient than agreed. So an AI model can never correctly reflect the contractual agreements. It is probably good for creating the baseline for a performance monitoring model, but it is not suitable for a fuel demand model.
Fantastic. Great answers, Peter and Joseph. So that just leaves me to thank you both for what was a great presentation and to Anexa for sponsoring this session.